everyone, welcome back to Easy Talim. If this is your first lecture in the series, my name is Irfan, and on this channel we are completing the entire Cambridge International A-Level Mathematics P3 syllabus completely free, topic by topic, exactly according to the 9709 syllabus. Today is part 2 of our logarithmic series, logarithm series. Last lecture we answered a question that many students never actually ask. Why do logarithms even exist? Because for years we were comfortable solving equations like 2 to the power x equals to 32, no problem. We simply ask, what power of 2 gives 32? The answer is 5. Then we saw 10 to the power 3 is 1000. Again, what power of 10 gives 1000? The answer is 3. Everything looked perfectly fine. Then mathematics gave us a very simple looking equation, 2 to the power x equal to 10, and suddenly none of our old algebra worked anymore. You can't factor it, you can't collect like terms, you can't expand it, you can't rearrange it. The unknown isn't multiplying, it isn't adding, it isn't inside a bracket, it's sitting in the exponent right here. And that's exactly where algebra breaks. So mathematicians created an entirely new function. Instead of asking what number is this, they asked what power created this number. That question gave birth to logarithms. Last lecture we learned something extremely important. A logarithm is not a magical button on your calculator. A logarithm is simply another way of asking what power. So if 10 squared is equal to 100, then log 100 to the base 10 is equal to 2. Those two statements are identical. One is written in exponential form, the other is written in logarithmic form. Okay, we also learned that logarithms and exponentials are inverse functions. So if f of x is e of x, then f inverse of x is ln x, right? The natural log. Just like addition and subtraction are inverse of each other, or squaring and square roots are inverse of each other, we also introduced the conditions that make logarithms possible. So for log x to the base a to exist, the base must be positive but not equal to 1, and the argument, this x right here, has to be strictly greater than 0, has to be strictly positive. These aren't random rules, they're consequences of how exponential functions behave, and these conditions become incredibly important when solving logarithmic equations, which is exactly what we are doing today. Now here's where many students make a mistake. They think, okay, I know what a logarithm is, chapter finished. Not even close. Knowing what logarithms are is like learning the alphabet ABC. Today's lecture is where we finally learn the language. Today we'll answer questions like, why does log xy equal to log x plus log y? Why isn't it? Why is this not log x plus y? So we'll come to this as well. Why can we move powers in front of logarithms? So for example, if x, which is in the argument, has a power b, we can rewrite it as b times log x. Okay, why do some logarithmic equations give answers that Cambridge refuses to accept? And why do students lose marks even after getting the algebra correct? By the end of today's lesson, you will be able to derive the 3 logarithmic laws, which is product, which is quotient, and which is power. So these are the 3 rules. Instead of just memorizing them, and simplify complicated logarithmic expressions, solve Cambridge logarithmic equations from the past papers, identify impossible answers before the examiner does, and understand why every step works. Because once you understand the reasoning, you'll never need to memorize these rules again. So let's begin with probably the most important page in this entire chapter, the 3 laws of logarithms. And unlike most textbooks, we are not going to memorize them first, we are going to prove where they come from. So last lecture we discovered something important. A logarithm asks only one question: what power? Today I'm going to show you why one of the most famous formulas in mathematics has to be true, not because Cambridge says so, but because it's written or because it's written in the formula booklet, but because math leaves us no other choice. Now if I write down log x times y to the base a is equal to log x to the base a plus log y to the base a. How many of you have memorized it? Now, let me ask another question. How many of you actually know why this is true? I'd rather that you guys give me the answers in the comment section. Now, remember, logarithms are simply the inverse of exponentials. We did that already, right? Wait a second. So logarithms are inverse of exponentials. So if we want to understand logarithms, let's go back to exponentials. So if I write down 2 power 3 is equal to 8 and 2 power 4 is equal to 16, and if I multiply them, what do I get? I get 2 power 3 times 2 power 4 is equal to 8 times 16, that is going to be 128, which is also 2 power 7, which is also 2 power 3 plus 4, right? Okay, so now let us circle or let us highlight this part. 3 plus 4 is equal to 7. Okay, so 3 plus 4 equals to 7. And now let me rewrite these exponential forms in logarithmic forms. And we have practiced that fairly well. So log x 8 to the base 2 is 3 and log 16 to the base 2 is 4, right? So let me replace this 3 and 4 by the logarithm. So this becomes log 8 to the base 2. This becomes log 16 to the base 2. And by, okay, so 128 was what? So 2 to the power 7 was 128. So I can rewrite this as log of 128 with base 2 gives us a 7, right? So I can rewrite this 7 as log 128 to the base 2, which is also log 16 times 8 to the base 2. Can you now see the connection? You need not learn it or memorize it because it is how the exponentials behave. Okay, now we can, so this wasn't really a coincidence. We can try another one for power of 3 for powers of 3, right? So now let's do, so 3 squared is 9 and 3 cubed or 3 power 5 is 243, right? So if I multiply them together, I get 3 squared times 3 power 5 is 3 power 7 is 2187. Okay, so 3 power 7 is 2187. Now what is log? So I can rewrite this as log 2187 to the base of 3, that becomes 7. And I can rewrite this as log 9 to the base 3 is 2. And I can rewrite this as log 243 to the base 3 is 5. Now we can see that 2 plus 5 is 7. So let me replace this 2 with log 9 to the base 3. Let me replace this 5 with log 243 to the base 3. And let me replace this 7 by log 2187 to the base of 3. Okay, now can you see that 2187 was a product of 9 and 243? So log 9 times 243 to the base of 3. And if I can remove it, you will see the connection right away. Okay, so this is, so we have the now this isn't happening because we got lucky. It's happening because, you know, exponentials already behave like this. So let us do, now that we have done a proof using actual numbers, let's prove it for any numbers. Let's do a general proof. Okay, so a general proof, so that you know that it is true for any numbers. Okay, positive of course. Now let's do log x to the base of a is equal to n. If I say so, then you will tell me that, okay, in exponential form I can rewrite it as a to the power m is equal to x. Okay, that's quite right. And log y to the base of a is, let's say it's n, so you can rewrite it in the exponential form as a to the power n is equal to y. Okay, that's right. If I multiply both of them, right, what do I get? I get a to the power m times a to the power n is equal to xy is equal to a over m plus n, right? I hope you guys all agree with me and you guys know the exponential rules already. I will also be posting a picture with all the exponential rules on my Instagram grid, where we go by the name of EASYTALEEM, which you guys should all save for future reference. Now, if I substitute back that m was equal to log x to the base of a, right? So now, so this is now, okay, if we do this, if I convert this into logarithmic form, this becomes log x y to the base of a is equal to m plus n, right? Now m was equal to log x to the base of a, log x to the base of a, and n was equal to log y to the base of a, and which, so whenever we have the like bases, we have the same bases. You can see that we had a base of a here, here, and here. Then if the logs are adding, you can multiply their arguments. So x and y will multiply together if the bases are same and the logarithms are adding. Okay, so that's the proof. You didn't have to memorize. It's just the exponential laws. Okay, now there's a huge Cambridge misconception. Let me show you the mistake that appears every single exam. So log x plus y, log of x plus y for any base. Now, can I split this? If I ask you this question, half of you will say yes. Now let's test it. Suppose x is equal to 10 and y is equal to 10. We also did that when this logarithm does not have any base, we take the base 10, right? Just like when x does not have any power, we take it for x power 1, right? Now, so this is going to become log 10 plus 10, that is log 20, which is approximately equal to 1.3010, right? Now, if you rewrite it as log 10 plus, or if you wrote it like log x plus log y, so this green part now becomes log 10 plus log 10, and log 10 is nothing but, so this is log 10 base 10 and log 10 base 10. If the argument and base are same, then this is just 1. So this is 1 plus 1, which is 2, and which is definitely not at all equal to 1.3010, which was log of 20. Okay, so clearly we saw that this cannot be true, therefore we'll put this not equal to sign here. Okay, so this is a false statement. Now the correct statement is that log of xy is equal to, is the sum of log of x and log of y. Now let's try to simplify log 2 to the base 5. This is the Cambridge style 1 marker question, plus log 15 base 5. Now since we have the same bases and the logs are adding, we can simply multiply the arguments of both the logs. So this becomes log 2 times 15, which is 30 base 5. So this is log 30 base 5, and we will leave the answer here. Now if I asked you to simplify 2 plus log 7 base 3, now you are going to get bamboozled. Okay, because one is a number, one is a logarithm, so these apparently they are not like terms, right? But we can convert them into those, right? Now you saw something, that this 2 was same as log 9 to the base 3. Similarly, this was also equal to, if I had written 4 power 2 is equal to 16, so I could also write log 16 base 4 is equal to 2. So I have quite a few options. However, in order for me to deal this 2 with log 7 base 3, I ought to convert this 2 into something which has a base of 3. So only I can put 3 square here, right, which is 9. So 3 raised to the power 2, so 3 raised to the power what gives me 9, right? So that's 2, right? So instead of 2, I can rewrite log 9 base 3. And when we are doing power rule, this is going to become very, very easy. Right now this seems like a guesswork, but it is really not, right? Okay, so now this becomes log 63 to the base 3, and you can put this in your calculator, and you can put this in your calculator as well, and you will realize that you are getting the same answer, right? But without making this, you cannot algebraically or numerically add this to each other, yeah, you can put the values in your calculator and get the result, but not do it without it. Okay. So yeah, so this is the sort of thinking that separates A grades from A star grades, right? Now we have proved something important. Multiplication becomes addition, not because someone invented a rule, but because exponentials already behave that way. Now let's ask the next question. If multiplication becomes addition, what should division become? Let's find out. So we have just proved that log x of y log x times y to the base of a is actually the sum of log x to the base a and log y to the base a. Multiplication became addition. Now I want to ask you a question. If multiplication became addition, what do you think division should become? Let's not guess, let's prove it. I know you guys said subtraction, but yeah, let's prove it. Okay, now if I can write 2 to the power 5 as 32 and I can write 2 to the power 2 as 4, if what is 32 divided by 4? So that is nothing but 2 to the power 5 divided by 2 to the power 2, which is 2 to the power 5 minus 2, which is 2 to the power 3, and which is 8. Now ignore the numbers. Look only at the exponents. So we can rewrite 2 to the power 5 upon 2 to the power 2 as 2 power 5 divided by 2 power 2, which gives us 2 to the power 3. Now what happened to the powers? We subtracted them, right? So 5 minus 2 is equal to 3, right? Because there were 5 2's in here, there were 2 2's in here, so we cancelled the 2 2's in the denominator with the 2 2's in the numerator, so we were only left with 3 2's in the numerator, right? So that's how the indices rules work. Now we can rewrite everything as logarithms. So this 2 power 5 equals to 32 may be rewritten as log 32 base 2 equals to 5, and this log 2 to the power 2 and this 2 to the power 2 equal to 4 may be rewritten as log 4 to the base 2 equal to 2, right? And we know that this thing right here, which was 8, so we can rewrite 2 power 3 equal to 8 as log of 8 to the base of 2 equal to 3, right? Now, so the exponents were 5 minus 2 equal to 3. Now 5 can be brought in from here, so this is log of 32 base 2. 2 may be brought in from here, so this becomes log 4 to the base of 2 is 2, and 3 may be brought in from here, so this is log 8 to the base of 2. So what has happened here? We did log 32 base 2 minus log 4 base 2 equal to log 32 upon 4 base 2, which is nothing but log 8 base 2, right? So right there. Now we can test another example, and I would want you guys to pause the video, do this, rewrite this working in your notebook, and do it for 3 power 6 equal to 729 and 3 power 2 is equal to 9. I want you guys to do it while we go ahead and do the general proof of it, right? Because that's how you understand your concepts, not just by consuming content for the heck of it, but doing the math in your notebook. Now let's prove it once and for all. Let's have log x to the base of a as m, so we can rewrite x as a to the power m, and let's write log y to the base of a as n, so we can rewrite y as a to the power of n, right? Now if we divide x by y, so x by y is going to be equal to a power m divided by a power n, which is nothing but a power m minus n, right? So x of y is equal to a power m minus n, right? And now we know that m was what? So m was log x to the base of a, and n was log y to the base of a, right? Now, so log of x upon y to the base of a is log of a. Sorry, what did we write here? So we wrote that this x upon y, which was a power m over a power n, was, so m was log x to the base of a and n was log y to the base of a. So we can rewrite this as x upon y is equal to a power m minus n. So I can also convert this into the logarithmic form so that this becomes log of x upon y to the base of a is equal to m minus n, and we already had m as log x to the base of a, so we will rewrite it here, x to the base a, and n was log y to the base of a, right? The order matters in division, in division and in subtraction, as you guys already know. So here is the general proof for the quotient rule. Now, it's exactly the same idea. We do the exponentials first and then logarithms second. Now, the biggest Cambridge misconception is that if, okay, let me explain it to you through using another, okay, let's try to expose this common mistake. So if I write down log x plus y divided by z to a general base, so that this is 10, right? Now, can I write this as log x plus log y minus log z? Half of you will say yes, but no, because the numerator isn't multiplication, it's addition. So that's a big cross. So we can rewrite it as, instead we can rewrite this as log x plus y minus log z. Okay? Now, if it was sorry, this is a bad color. Okay, so if we had log x times y divided by z, so now this I could rewrite as log x plus log y minus log z. Now this is true, but not this one. Okay, this is a big no. So always simplify multiplication and division, never split addition or subtraction. Okay, now let's do a Cambridge example. So log 50 to the base of 7. I should change color. So log 50 to the base of 7 minus log 2 to the base of 7, because the bases are same. Just like in the case of exponentials, we can treat the argument so that this becomes log 25, which is 50 divided by 2 to the base of 7. Pretty easy. This is your final answer. No calculator needed. Now, if you had to simplify log 3 of x to the base of 5 minus log x minus 1 to the base of 5. So this is nothing but 3x divided by x minus 1 as the argument for logarithm, which has a base of 5. Okay. Now, can we cancel the x's? Of course, no. They're not factors. They're different algebraic expressions. So this right here is the final, most simplified answer. Now, let me give you a mini challenge. Okay. Take out your notebooks. I'll give you 20 seconds. You have to simplify log 48 to the base of 2 minus log 3 to the base of 2 minus log 2 to the base of 2. Now you can also reread it. So we will divide, so since the bases are same, we will divide this 48 by 3 and by 2. And now you will ask me that why can't we divide this 3 by 2? I'll tell you why. Because what if you just took the minus sign as common? So now you will have this. So this bracket becomes log 6 to the base of 2. And now you have log 48 to the base of 2. And which is subtracting. So the arguments are going to divide 6, which is a product of 3 and 2, right? And this entire fraction is the argument for the logarithm, which has a base of 2. So I can rewrite this as log 8 to the base of 2, and log 8 to the base of 2 is nothing but 3. And we are now going to come to the power rule, in which we are going to explain to you. So we have done multiplication, that became addition in logarithms. We did division, we did subtraction of logarithms, which divided the arguments. Now there is only one exponent left, which is going to explain to you that why log 8 to the base of 2, which is nothing but log 2 cubed to the base of 2, is actually 3, right? What happens when a power sits outside? So it comes in front of the logarithm. Let's see whether logarithms copy that behavior as well or not. We'll prove that now. This This one right here is probably the most misunderstood law because students remember it as bring the power down. I don't want you guys to remember it that way. I want you to understand why the power comes down. So we have proved two logarithms. Addition of logarithms multiplies the arguments if the bases are same of those logarithms, and subtraction of those divide the arguments of the same base logarithms. Okay, now there's only one exponent law left. What happens when we raise something to another power? So let's write down 2 to the power 3 and the entire thing raised to the power 4. What happens here? Of course, we know that we multiply the powers inside and outside the bracket, so this becomes 2 power 12. So we can say that 3 times 4 is equal to 12. Okay, now let's see whether logarithms behave in exactly the same way. Now, if I write down 2 power 3 is equal to 8, and if I raise both the sides to the power of 4, so what does this become? Right? So this becomes 8 power 4 is equal to 2 power 12. So, but what is log 8? So if I do log 8 to the power 4 to the base of 2, then this is nothing but this exponent, which is 12, right? But and what is 12? 12 is 4 times 3, right? So 4 times 3. So log 8 power 4 to the base of 2 is 4 times 3. Now what was this 3 actually? So 2 to the power 3 was 8, right? And we can rewrite this as log 8 to the base of 2 is 3. And instead of 3, I can rewrite this log 8 to the base of 2, right? So here you go. So this is log 8. The argument with the power 4 becomes a coefficient of the logarithms with the same base, right? So notice what happened. The power came in front of the logarithm, or it became the coefficient. I will give you another example, but I want you guys to do it by yourself. Prove it yourself. 3 square equals to 9. And 9 cube is equal to 3 power 6. I want you guys to use this in order to prove this exponent rule. You have this screen right in front of you. Take a screenshot and try to do this boxed example yourself while I proceed to do a general proof. Okay, now let's prove it properly. So log of x to the base of a is equal to m, and therefore in exponential form, I can rewrite x as a to the power of m, right? Fair enough. Now, if I raise a power m to the power, okay, let me use another color. If I raise this a power m to the power of k, and therefore I have to do the same thing here as well. So I have a power mk is equal to x power k. Now, if x power k is a power mk, what logarithm gives mk? So of course, log x power k to the base of a is equal to mk, right? But m was what? M was log x to the base of a. So I can rewrite it as log x to the base of a, which was m. So this is same as log x power k to the base of a, and here is your general proof. Now I want you guys to do it one another way as well. Now we are proving here that log 16 to the base of 2 is log 2 to the power 4 to the base of 2, or rather let me do 81 here, right? So this becomes so this becomes log 3 to the power 4 base 2, and this is 4 times log 3 to the base of 2. Now I can also do it this way. So log 81 is what? It is log 3 times 3 times 3 times 3 base 2, and applying the product rule I can rewrite it as log 3 base 2 plus log 3 base 2 plus log 3 base 2 and plus log 3 base 2. So this is what? These are 4 similar terms, so I can rewrite it as 4 times log 3 base 2, which is same as here, right? So what's the meaning of this? We understand something very important here. The power didn't magically jump outside and came here. The exponent law forced it outside. Logarithms simply copied what exponentials were already doing. Now let me show you the mistake that appears every year. So if I write down log x to the base of 2 square, can I write it as 2 times log x to the base of 2? No. It's a huge no. The power is on the logarithm itself and not on the argument. right? Not on the number inside. So we have to, so the rule is that if the argument has a power, so this entire highlighted part is the argument of the log. If it has the power 2 into any base, then we can bring this power down, right, and bring it in front of the log, or make it the coefficient of the logarithm and removing the power from the argument, right? Another misconception is that if you have log 3x power 2, then where is the square? Is it inside? Is it outside? Right? This actually means that it is log 3x whole square, right? Because the logarithm is evaluated first and not the square. It does not mean that it is log 9x squared unless the brackets are written that way, okay? So make sure that you are really given, so it would be such a case if you had log 3x squared and then so this, wait a second, so this is square, these parentheses are for this power, and these darker parentheses are for the argument of the logarithm. So now clearly 2 is the power for the argument, so you are going to bring it back and turn it into log 3x with a coefficient of 2, okay? This tiny difference has cost students marks in Cambridge exams, and it has come repeatedly in the examiner reports. Now, if I ask you to simplify log 7 base 5 times 3, right? So the answer is nothing but log 7 cube, which is 343. So I will write it down, 343 base 5. So this is the simplified version. Now, if I ask you to expand completely this term, so this is log x squared y5 over z cubed to the base of 3. Now I can see that these are multiplying and dividing, so I can rewrite it as log x squared base 3 plus log y5 base 3 minus log z cube base 3, and I can now bring the powers down. So this becomes log 2 times log x base 3 plus 5 times log y base 3 minus 3 times log z base 3, and that's your expanded form. Notice the order. We did the quotient first, then the product, then powers. Don't randomly move powers before separating terms. Develop a consistent method. Now I'll give you 10 seconds and you have to simplify this. I will change color, so your time will start as soon as I would have written this, and I will not wait for you guys' answer. You can submit those in the answer section, right? I'm not going to tell you what it is. You can send the answers to me over in my DMs on Instagram, where I go by the name of EASY Easy Talim, TALEEM. Now, we have built the entire toolkit, product rule, quotient rule, power rule, but here's the real question. What do we actually do with these laws? Of course, the answer is we use these to solve logarithmic equations, and that's where students begin making mistakes that cost them full questions. Let's solve some genuine Cambridge style examples now.